Hello, today we're going to look at trigonometric integration, and this will be using certain techniques to solve integrals that involve specific forms of our trig functions. Okay, so we'll dive straight in, and we're going to start by looking at integrals of this form. So we have a power of sine and a power of cosine. The power of sine is m, the power of cosine is n. And we're going to look, depending on the values of m and n, how we might go about integrating that. Okay, so we take the key idea from the book. It's a pretty big one, so we break it down into two pieces. Okay, and in the first instance, we'll assume that m is odd. That specifically means that the power of sine is odd. Okay, well, if m is odd, we can rewrite it as 2k plus 1, so 1 more than an even. That makes it an odd. And doing that, we can kind of break apart these powers of sine and essentially take one of them out. Okay, so here we've got sine squared x to the power k, that's the even piece, and then the one more here. You'll also recall that sine squared is 1 minus cosine squared, so we can do a substitution here, replacing sine squared x with 1 minus cosine squared x. And in particular, because we've got this odd m, we're going to make the substitution here that u equals cosine x. Okay, so it's the other one, right? The sine is the odd power, so the substitution is going to be the other, the cosine. And because u is cosine x, we get du is negative sine x. And then if we look in here, we take the even power of sine and make it a 1 minus cosine squared to the power k. And then this extra sign here will disappear when we make the substitution, right? We have sine x dx, that's going to be replaced by the du. And what we're left with in here is just powers of u and a du, which we can then integrate. And we'll see that in an example. Okay, so we'll also look at a similar example. Let's suppose now that the power of cosine is odd. In other words, the n is odd. Well, now we're going to use the substitution u equals sine x. Okay, so again, because the cosine has the odd power, the u is going to be the sine x, and then du is going to be cosine x dx. And again, it's going to work out pretty similarly. We take the power of cosine, we take one of them out, and that sort of gets replaced with this cosine x dx. And the remaining powers of cosine are even, therefore can we use this trig identity that 1 minus sine squared is cosine squared, and we're left just with powers of u. And again, we'll see an example just to see how this works. It's a little hard in the abstract. Notice we've said if the power of sine is odd or the power of cosine is odd. If they're both odd, we can actually use either of the first two parts of the key idea. It doesn't really matter which one we use, it'll work out fine. But of course, what we're left with is what if they're both even? Well, if they're both even, we actually reduce the powers. We use these two trig identities. The cosine squared is 1 plus cosine 2x over 2. And sine squared x is 1 minus cosine 2x over 2. That reduces the powers. We then have to expand. It can be a little intricate and complicated. But it does eventually get to the point where we only have odd powers or even powers we can deal with. Again, we'll see an example of that. Okay, so just as a recap for that, if the m is odd, we're going to use u equals cosine. If the n is odd, we're going to use u equals sine. If they're both odd, we can have u equals either, it doesn't matter. Whereas if they're both even, we're going to have to use these identities. Okay, so it's probably time we saw an example. Okay, and here's our example. We have sine to the power 4x, cosine to the power 5x, and hopefully we recall from what we just saw that because the power of the cosine is odd, we're going to have u equals sine x. Okay, so we'll let u equals sine x, and therefore, of course, du is cosine x dx. Okay, we'll do a bunch of algebra on this. So the sine to the power 4x will leave. The cosine to the power 5 here, we're going to break up. Okay, it's really cosine to the power 4 times by cosine. Well, 1 cosine will leave, but the cosine to the power 4 will make 1 minus sine squared squared, because it's cosine squared squared. And now everything will simplify because we have this substitution. We can just make the sine to the power 4 u to the 4, and sine squared here u squared, so we get u to the 4, 1 minus u squared squared. And of course it's du, that's important. Okay, and this looks a lot simpler now, right? It's just powers of u. We've got a du. This isn't too bad. We were just given this integral. It's pretty straightforward. We still, of course, have to distribute all the u's. So we square here, FOIL this piece, and then distribute the u to the 4. We get this. And again, this is a very simple integral, nice polynomial. I'll just bring it up here as we go onto a new page just to remind ourselves what we're doing. So here's our integral, which we can very easily integrate. So u to the 4 minus 2u to the 6 plus u to the 8 integrates to u to the 5 over 5 minus 2u to the 7 over 7 plus u to the 9 over the 9, and of course the constant of integration. And then our final step, notice, and we still have it here, that the u is sine x. And because u is sine x, we can just plug all that in, and here we get our solution. And so that is the integral of sine to the power 4x cosine to the power 5x. Okay, that's not too bad. So we did the right substitution. Okay, we'll take another example, and this will be a bit more intricate. I'll not do every step in this example because it can get quite long. But now we have both the powers being even. The power of cosine and the power of sine are both even. Just a reminder, so we'll put that there. Just a reminder what the two trig identities are for reducing the powers. Let's bring those in there. But this simplifies here. Okay, we get 1 plus cosine 2x over 2, and then we get 1 minus cosine 2x over 2 for the sine, and that's squared because it's sine to the power 4. Okay, so the next step, well, I'll bounce ahead a little bit. We'd have to FOIL here and distribute this, and we can notice we have 2 on the bottom, then a 2 on the bottom here, which is squared, so we get 1/8. But trust me, this distributes to this. Okay. Well, we've made some progress, but there's still quite a bit to do here. We have, 4 terms here, all added or subtracted. And I think what I'll do is just integrate each one individually. Okay, particularly the cosine squared and the cosine cubed. It's going to take a little bit of work. So let's just take each piece. And this is sort of scratch work, right? This is something we do on the side and integrate each piece. Well, the first one's pretty easy. We just integrate the 1. Well, it's x, that's about it, really. I've included the constant of integration here. Now clearly when we bring them all back together we'll only need one constant, 1c, but just throw that in there to be correct. Next we'll do the negative cosine 2x, and again that one's actually pretty straightforward. That's going to become negative sine 2x over 2. Next up we have the negative cosine squared, and again we're going to use the power reducing identity here. What's called the double angle identity. Just a quick note, we have a 2x here, it's cosine squared 2x. So when we apply this, we have to double this 2x, so we get a 4x here. That's why this is a 4x. But again, once we've reached this stage, this is fairly easy to integrate. So we get the minus 1/2, the 1 integrates to x, and the cosine 4x is sine 4x over 4. Okay, so that's the first 3. Just a reminder of what we're doing, that's the integral there. Okay, the last one, the cosine cubed 2x. Well, actually, this is back to key idea number 1. We have an odd power of cosine. And it just so happens we don't have any sines here, but we still have an odd power of cosine. So it's a nice little example of our first key idea. We have an odd power of cosine, so we can break that apart, take the even piece, the cosine squared, and then sort of have one left over cosine 2x here. And now we're going to do 1 minus sine squared 2x is the same as cosine squared. And if we do our substitution, remember our substitution this time is going to be u equals sine 2x. And so it all simplifies a little bit to 1 minus u squared du. Okay, so we integrate that, we get u minus u cubed over 3, and of course finally we did say that u equals sine 2x, so we have to plug that back in. So we get 1/2 sine 2x minus 1/3 sine cubed 2x plus c. Okay, so we've integrated 4 separate pieces. I'll just put them in the corner here, pretty small, but add them all together. And so we bring them all together and simplify. We get that this integral is equal to this. And I say I've just simplified there by adding them all together, but that's not the hard part. So sure enough, this is the integral of cosine squared x sine to the power 4x. Okay, and that's not too bad. Now I say there's a lot of pieces there. We had to break it down. We've got 4 separate integrals, do them all separately. It's not too hard, but you do have to be very careful to keep each piece separate and clear. So I say, I sort of went through each integral individually. I recommend you take some scratch paper and do each one by itself, and then sort of bring it all back together as I did here. Okay, so that's the 2 even cases, and that's probably the hardest. There's one other type of trig integral we're going to look at here, and these are thankfully a little bit easier. So this is, instead of having powers of x, so powers of the trig functions, we're going to get multiples of the x. So there's basically three possibilities. We're going to have sine mx, sine nx, so two sines, cosine mx, cosine nx, or the sine mx, cosine nx. And all three of these cases are very simple, as long as we just bring in these trig identities. Okay, so we've got these three trig identities. Obviously, each one applies to each one of the above. And using the trig identities, instead of these being multiplied, essentially we have two sines or cosines summed, and that's much easier to integrate. So if we take an example, cosine 4x, cosine 5x, okay, and for this one we'll need this particular identity, and using this identity is very straightforward now. We get kind of the m minus the n and the m plus the n, and so we're going to get cosine x plus cosine 9x. Notice actually this could be a minus or a plus, it doesn't matter, it depends which way around we put it, because this could be 5 minus 4 or 4 minus 5, it doesn't matter. And the 9x obviously is just 5 plus 4, and now to integrate this is very straightforward. We're going to get sine x plus sine 9x over 9, and that's about it. So I say those types are a little easier, as long as you have those three identities, which maybe we'll put here one more time, we can always integrate those pretty easily. There are a couple more examples in the book how you can use this with tangents and secants, but that'll probably do for us for now.